Okay, welcome back everybody, Math 107. We're at Lecture 16A. Yesterday, or last class period, we looked at compounding as an application of the exponential growth function, and then we jumped into saying, okay, compounded continuously is a very good approximation of compounded daily. Being pushed for time, I didn't derive that formula for you. It's in your textbook. But it's always a nice, easy, quick way to make a good approximation. How much money do you need in an account today so that you can have so much in the future? If your bank was giving you like 4% compounded daily, you could use the quick formula shampoo, PE to the RT, to get a good approximation to figure out how much you need. So that's a nice little easy, quick formula. All right, today we want to move on into 4.8, and we're going to look at some growth and decay, and then we're going to look at the cumulative review on page 501 and 502. Hopefully all this gets done in 16A, and then when we start lecture 16B, we'll be into our trig, which is the rest of the semester. All right, first of all, before we start, I want us to just do a quick recall that when we have our compounded continuous formula, we use that the future amount is equal to the present amount e to the RT. This was when you had compounded continuously. And T represented what? Time in terms of years. And R was the rate you saw named in the problem, and the P represented the present value, the amount you put in, and A is future amount. So if you have any one unknown here, any one unknown, you would know how to solve for the other. For example, you might know A, but not P, and then you would just be solving an equation. Or you might know A, P, and R, but have to solve for T. How long does it take your money to accumulate to a certain amount? Or you might need to know at what rate you're being charged. All right. Now, in section 4.8, we're going to talk about the uninhibited growth. Oh, by the way, remember your growth curve looked like this when you had this. Goes through the point 0, 1. All right, in 4.8, we're going to first talk about uninhibited growth, a population with uninhibited growth. And that just means that it's going to keep growing forever and ever and ever, and it never slows down. Again, most things in life eventually slow down due to crowding or something like that, and that comes in under what is called logistic models, but that's not an objective of this course. So really, in theory, this is just something that's going to grow forever and ever and ever. Well, if it's going to grow forever and ever and ever, the difference now for section 4.8, we're talking about a real population, so we wouldn't be talking about negative, so we'll take that little part of the graph off. And this is uninhibited growth, just going forever and ever and ever. This formula right here works absolutely perfect, except that your book is going to give you the formula A equals A sub 0 e to the kt. And these are just symbols in your formula, so if you just want to remember shampoo, shampoo will always work. A sub 0, well, that just means that whenever t is 0, whenever t is 0, e to the 0 is 1, so you're talking about your, at time equal to 0, your present value. So A sub 0 is your initial amount in your population. So whenever k is greater than 0, which is the same thing as your r up here, you're going to have exponential growth. Okay? All right, such as sales or whatever.
In the first graph you have like 0 and 1 and continuous. In the second graph you cut it out?
I cut it for 4.8 because we're this is the coordinate system x, y kind of deal. These are negative numbers. So if you're talking about bacteria, we have to start talking about 0 or more bacteria. We can't talk about a negative number of bacteria. So that's why you have a restricted domain when we're talking about a population growth. Thank you for getting that clarified. Anything else? All right. So we'll first look at a population growth uninhibited, and we'll work a couple problems together. We'll head over to page 482, and I pulled two growth problems on this, and we'll see how to work the problems. I think we're good at it. Just plug and chug if you follow the words. We're on page 482. We'll just look at number 1. That's because I think number 2 is a web assign. Give you some extra practice in number 2. Can we zoom in on that a little bit? Great, thanks. All right, we have the growth of an insect population. This especially seems to be the case in the summer. Let the size P of a certain insect population at time t, and they have to tell you if this model, this is called a model, your equation, was set up in terms of days, years, or whatever. Whoever they paid a lot of money to, some mathematician, to come and figure out this model by collecting a lot of little samples and stuff, they defined the size of the population in terms of days. So we're told what it's defined in terms of. So the function is P of t equals 500 e to the 0.02 t. So somebody was paid to come up with this formula that describes the insect population with respect to time. Okay? All right. So let's write the formula down. P of t equals 500 e to the 0.02 t. All right, so if you'll have your book open, and we'll just go from here. First question is the number of insects at time equal to 0. What is the number of insects? What does P represent?
Future. This initial.
Okay, P is the size of your population, right, at time t. P is size of population at time t. So question A says, determine the number of insects, which is the size of your population, at t equal to 0. At t equal to 0. So where are you putting the 0, everybody? In t. So you're looking for P at 0 equals what? Can you just look at it and already tell what the answer is?
Yep.
Yeah, it is 500 because put a 0 in for t. You've got 500 e to the 0, and e to the 0 is 1. 500. When you have it in this form, this value right here, if you look back at that little formula, is the a sub 0 e to the kt, or if you're looking for shampoo, p e to the rt. This will always be your initial size, how many you're starting out with. Okay, everybody good? Okay, problem 2. Part B, excuse me. Part B. What is the growth rate? Growth rate. Okay, let's relate it to the money problem. The amount of money is the shampoo. When we put money in, what was our rate of growth on our savings account? Where did you find it? That was your R value, right? And these, now we just have a little K that represents the same thing as the interest on your account. It means how it's growing, growth rate. So what would everybody say the growth rate is? 0.02, or how do you write that as a percent? 2%. So we've got a 2% growth rate. Okay? Does that make sense? Okay. We're not going to use a graphing utility to graph this. We're just going to get a little feel for what it might look like. Along this axis I'll have t. Along this axis I'll have the size of the population. What's my intercept here on the y-axis, or in this case the p-axis? What's the intercept? What goes on this? 500. Okay, and we start out with 500 insects, so we won't have anything where the t is negative because we're not going back in time. This value right here is positive. You could plot some points. You could let t be 1, 2, 3, and plug and chug in your calculator. But the idea is that because this is positive, your curve is going to grow like this. Okay, it's just growth. Okay, we just want you to have a visual of what it's going to look like. Okay, everybody good so far? Okay, let's go to D. Let me rewrite this. P of t equals 500 e to the 0.02 t. Okay, D says, what is the population after 10 days? What is the population after 10 days? How are you going to do that, everybody? Yep, we're going to find the size of the population when t is 10. 500 e to the 0.02 times 10. 500 e to the 0.2 power. 0.02 times 10, 0.2. And then you have your little calculator. And it looks like that you have 610.7 insects. All right, I'm hoping somebody's going to go, how do you have a 0.7 of an insect? I guess that's one in the making, huh? Are you cut off part of them? All right, I think you would just say approximately 611 whole insects. All right, since these are real things, I don't think we can have part of something. So the population after 10 days, it's about 611, might be 610. Okay, and again, this is a model that describes the behavior. It doesn't mean that it's going to be an exact match, but it's following it pretty closely. All right, everybody good so far? 611 insects. E, when. When you hear the word when, what are you going to be looking for? Find T. When will the insect population reach 800? What are you going to do here, everybody?
800.
Okay, the size of the population sometime or another is 800, so we're going to have to solve for t. So we have 800 equals 500 e to the 0.02 t. Name the type of equation this is. Verbalize it. What is it? Exponential equation. And our unknown is going to be up in the exponent. What does that tell us is going to be involved in solving this? Go to logs. Exactly. All right, so we're solving, and let me just make a little note. Exponential equation. All right, what's going to be my first step, everybody? Do I jump right on natural log?
You moved the 500.
Okay, we've got to have a 1 in front of this E. I'm going to mark that in red because, oops, that's blue. Because y'all told me that yesterday. And you didn't send it to your long-term memory. Divide by 500. Okay. All right, so we have 8/5 equals e to the 0.02 t. All right, remember that coefficient in front of the e before you go to exponential log form, you need to have a 1 there. Do you need to pass this red pen around? You pass that around. I want y'all to mark it in red. All right, now you won't miss it on the test. Just write me a note on the test and say, Ms. McCollum, notice I didn't miss this. All right. So now we have that exponential equation. I got the 1 in front of the e. What are you going to do, everybody? You can, remember there were 2 ways you could do this. You can either take the natural log of both sides, or you can convert to log form. Which way do you want to go?
Natural log.
You want to take natural log of both sides? Natural log of 8/5 equals natural log of e to the 0.02 t. And this involves your identity. The natural log of e to the 0.02 t is what? 0.02 t equals natural log of 8/5. So t then is equal to natural log of 8/5 divided by 0.02. Now, let's make a note. I meant to do that in a different color. If test says exact value, then just leave it like this because you don't have a calculator. I'd put, if you weren't using a calculator on your test, then this is as far as you go. I mean, how can you guess what the natural log of 8/5 is? I mean, you could start guessing and kind of figure it out, but just feel free to stop right here. Of course, if you have a calculator, you would like to know about how long it's going to take 800 of these little insects to appear. So you can go to your calculator, and we'll get the natural log. And be careful you use parentheses around 8/5, order of operations. The natural log of 8/5 divided by 0.02, and I'm going to get 23.5. 23.5 what? What's my units? Days. Because your time is expressed in terms of days. Okay, so if you were working for the county or whatever and the insects were going crazy and you needed to know how much insect spray to buy, you could kind of figure out, well, these things are going crazy. In 23 days, I'm going to have 800 of these. These are probably in thousands, by the way. 800,000 of these little things flying around. I would know about how much insecticides to buy or whatever. All right, everybody good so far?
I have a question.
Yes.
Part C.
Part C.
Yeah. Do we have to like get just like the other side? Do we have to get the points, or can we just like approximate and make it?
Oh, for part C, like if I were asking you to graph this on a test, you would need to know this intercept and show that it's just a growth curve. Yeah, or, I mean, if you had a calculator, you could get some points, but for me, I'm just needing to know you recognize that's a growth. Is that good? Okay, let's go to part F. Part F. And the problem again is P of t equals 500 e to the 0.02t. All right, the question is when, so we're going to be looking for a t, will the insect population double? And this goes back to the money problems we did yesterday. Everybody wants to know, how long is it going to take for my money to double or my money to triple or whatever. So this says, when will it double? Okay, so what are you going to do? Yeah, if you start out with 500, if you're going to double it, you just put 1,000 equals 500 e to the 0.02t. And when you divide by 500, you got 2 equals e to the 0.02t. And by the way, if you didn't even know what the initial size was, just like I noticed in some of your homework problems, it says, how long does it take money to double at a certain percent? Well, it doesn't matter if it's 500 doubling to 1,000 or $1 doubling to $2 or a million doubling to 2 million. When you divide here, this number will always come out to be 2 if it's doubled. So when you have one of those vague questions in your homework, how long does it take something to double, you can make up any number you want. Okay? All right, so now we're 2 equals e to the 0.02t, and everybody's telling me to do what? Natural log of both sides. And then your identity, the natural log of e to the 0.02t is 0.02t. And so the exact answer is natural log of 2 divided by 0.02. But we want to have a better feel for what that is. Natural log of 2 divided by 0.02. And it looks like it's going to be approximately 35 days. So about every 35 days, your insect population is going to double. Is that good? That seems easy after all the stuff you guys have been through in this course so far, doesn't it? All right, let's go to problem number 7. Okay, one of the reasons we're going to do number 7 is I want you to watch the words. Problem number 7. This is on page 483 at the top. First of all, it's telling you it's the population growth, and it's telling you that it follows the exponential law. Okay, if your question is not clear, then you don't really know what kind of model to do. A lot of times it will say it follows uninhibited growth. All right, I'm just going to switch around to you on number 5 at the bottom of the previous page. The population of a colony of mosquitoes obey the law of uninhibited growth. That just means that they start and they just keep on multiplying like crazy. Okay? All right, question 7. Watch the words. The population in this southern city follows the exponential law. All this means is the same old, same old. It's going to be a sub 0 e to the kt. Okay? If the population doubles in size over an 18-month period and the current population is 10,000, what would be the population in 2 years? Do you see 18 months and then the word 2 years? So we need to make sure how we're defining our t. All right? Everybody got the question? All right, so if you know in number 7 that you're following an exponential law, the first thing you're going to write down is what? You're going to put down your formula, which is A, it could be shampoo or whatever you want. A equals a sub 0 e to the kt. Okay? All right. This one says that you're starting out with a current population of 10,000. Where does that go in this problem? A sub 0. If you start out with 10,000, it says the current population is 10,000. Okay, current population is 10,000. Okay, we're going to put t in years. Okay, the population doubles in 18 months. Doubles in 18 months. So if it's going to double, you're going to have 20,000. And what is t when it doubled, if t is in terms of years? $18 months, how do you express that in terms of years? 18 over 12, and what does that equal to? 1.5 years. Okay, so we'll put a 1.5 up for t. That little piece of information is going to help me find the k, the growth rate, right, of my population. Because the question says what will be the population in 2 years. So this first piece of information helped me get in here to solve for the growth rate. Because this is our formula, but we got too many unknowns. We don't know the k, the t, or the a. Too many unknowns in here. All right, so let's solve for k. Is everybody with me while we're doing this?
Why aren't you using the shampoo formula?
Say it again?
Why aren't you using the PERT? Isn't it the same thing?
Yeah.
You could use either, it doesn't
Yeah.
matter.
Yeah, her question was, why didn't I just use p e to the rt? And that would be absolutely fine. The only reason I'm not doing that is because I thought if I did, people were going to send me emails saying, well, the book uses an A. So you can just always do p e to the rt and you're fine. All right, so now we're going to solve for k. We'll divide both sides by 10,000, so we get 2 equals e to the 1.5, whoops, k. Sorry, 1.5k. Same old, take the natural log of both sides. So natural log of 2 equals 1.5k. K is natural log of 2 divided by 1.5. Let's see what that comes out to be. Natural log of 2 divided by 1.5. And that's about 0.462. Okay, so for this particular southern city, it looks like it's growing at 46%, kind of a pretty big population explosion. Well, of course it is. If in a year and a half you double your population, that's pretty fast. You're not doubling your money anywhere in a year and a half. All right, unless you're out on some streets doing some things you shouldn't be doing. All right, so this information helps me rebuild my formula. A is 10,000, e to the 0.462 t. All right, so now I'm ready to answer the rest of the question. What will be the population in 2 years? So what do you do, everybody? Just plug in a 2. So let t equal 2 and solve. All right. Okay, we're good on uninhibited growth? Uninhibited growth. All right, let's go to what we call decay. Decay. Okay, and I'm back on page 473, by the way. Just wanted to make sure you're wearing out your textbook. This is the bottom of page 473. This was your growth. Notice K is greater than 0. K is greater than 0. It's a positive constant greater than 0. Okay? All right, let's go to the decay, which is on the page 475 at the bottom. Uninhibited decay. This just means that there's not going to be any leveling off until it just about runs out. And it's going to approach 0 because we would know what this would look like. All right, in this case, K is a negative number. So I want to just play around with that a little bit to say you already know all about this. All right. Decay. All right, the book says A of t equals a sub 0 e to the kt, but k is a number less than 0. Let's go back to what you already know. Recall, when you had y equals a to the x, back when we began studying exponential functions, whenever a was greater than 1, your curve went like this. Y equals a to the x, when 0 was less than a, less than 1, your curve looked like this. A was a fraction. Remember, like 1/2 to the x? Example, y equals 1/2 to the x. Your curve looked like this. Okay, because you know as you raise a half to a bigger and bigger power, the number gets smaller and smaller. All right, I want to take this a step further and rewrite this as y equals 2 to the negative 1 raised to the x. 2 to the negative 1 is a half, which is 2 to the minus x. Okay, the whole reason I'm sending you on this little route is to give you the good understanding why they're calling a sub 0 e to the kt as a decay problem if k is less than 0. Time can't be less than 0, k less than 0. Well, that all comes from when we studied the exponential function where a was a number between 0 and 1. If I rewrote this with a base 2, notice I had that negative exponent there. And that was really 2 to the negative 1 times x. So when this k is a negative number, basically you're looking at like 1 over e, 1 over 2.72. So that's why you're going to have your decay. Now again, this is a population that we're talking about. So we wouldn't be going in negative time. We would start only when t is greater than or equal to 0. We'll just be looking at it decaying like this. Yes?
E has to be a fraction for it to be a decay. Is that what you're saying?
1 over e, right.
Okay.
And that's, if the k is negative, that's going to make it a 1 over e. Is that good? Okay, so we'll have a decay. The questions look very similar to the other, except now we have a decay. It's called uninhibited radioactive substance. And instead of talking about doubling time, we talk about half-lives. Half-lives of radioactive substances. If you start out with 1,000 grams of something and its half-life was 10 years, how much do you have after 10 years? If you start out with 1,000, 500. Just keeps cutting it in half. Half-life. Okay? All right. So let's go to the exercises. We're on number 3. And you can still use your P e to the RT. You can still use your P e to the RT, it's just your R is negative, if you want to do that. Okay, number 3. We're talking about strontium-90. It's a material that decays according to this equation. Notice that your K, or your rate here, is negative. That means, really, if you rewrote that with, can you zoom in? There we go. All right. It means that if you tried to write that without a negative exponent, you got your 1 over E. So that's how you know it's decay. A sub 0 is your initial amount. T is in years. And the scientist has a sample of 500 grams. So they started out with 500 grams. They're making, they're collecting some data, and they paid him a lot of money, and he came up with the formula. All right, this is how people make money. All right, so we've got the question in mind. Let's see if we can make a sketch, work the problem. Okay, this is page 482. We're looking at number 3. And we have A of t equals A sub 0 e to the negative 0.0244 t. Okay, again, because you have the negative right here, you know it's going to look like this. Will this thing ever equal 0? Will e to some power ever equal 0? No. So what's going to happen is it's going to get very close to 0, but it never totally gets gone. There's always just some minor trace. It might be so small you can't trace it, but it never reaches 0. It approaches 0.
X equals 0 is like an asymptote, in other words.
Yes. The x-axis here, or in this case the t-axis, is your asymptote. Excellent. Okay?
So what's that? T and...
This is the t-axis, and this is the amount. Because your function A is a function of t, and t is in terms of years. And A is in terms of grams. Okay? Alrighty. If you start out initially with 500 grams of this stuff, where's the 500 go? A sub 0. So we have A of t equals 500 e to the negative 0.0244 t. Okay, question A. What is the decay rate? What would everybody say? Negative 0.0244. How do you write that as a percent? 2.44% negative. Negative 2.44%. Okay. If I were going to graph this, and we would just be doing a basic graph, what goes on the a-axis here? 500. And the curve is just going to come around like this. Okay? How do I know it's coming down like this? The negative exponent right there.
So is it always going to have that shape?
Mm-hmm.
Like that?
It might be dropping a little faster or flattening, taking a little longer.
Is it ever going to cross the...
If it crosses the t-axis, there'd have to be a place that this value equals 0. Will this A ever equal 0?
No.
So it can never be 0. E to some power is always positive. A positive times 500 is always positive, so it can't possibly cross the t-axis. Very good questions.
Thank you.
Everybody good?
How do you know it's supposed to be steeper, like the graph, if it's supposed to be like going down faster or like?
This number right here is going to tell you if it's going to go fast or slow, and that's a very small number, so it's just going to crunch down real slow. But just to get a feel for it, you could set up a little chart and put numbers in and punch away on your calculator. But if this were like -3, it's going to drop really fast. But that's a real slow decay rate, real slow, 2%. Like think of like 2% a year, dropping 2% a year, going from 100 to 98 to 96 to 94. Does that help? Okay, everybody good? All right, so that was B. Okay, how much of this is left after 10 years? We're on part C. How much is left after 10 years? What do you do?
Put in 10, 15.
The amount, when you start out with 500, e to the negative 0.0244 after 10 years when t is 10. So let's see what we have after 10 years. Probably still have a whole lot of this stuff. 0.0244. Be sure you make that negative. Forgot to do that. Times 10. I'll just make it now. Negative. Whoops. I think I'll start over. Okay, negative 0.0244 times 10. And then I'm going to raise e to that power. And then I multiply times 500. And so in 10 years, I'm still left with approximately 392 grams of this. So you see it's not going away very quickly. Is that good, everybody? All right, D. When will 400 grams be left? When? What am I looking for? T. Okay, so you're going to have 400 grams, and we wonder when in the world that will happen. By the way, if you have a radioactive substance and there's a leakage somewhere, and they know the half-life and etc., they need to know when is it going to be at a safe level so people can come back in, or if you had to evacuate people, they have to know how long it's going to take this to break down the radioactive substance before it's safe to come back. Or, when there's spills along the highway, they'll shut down a highway sometime for a certain amount of time because they figure out how long is it before it's safe to get back. If it's a radioactive substance, its concentration will be decreasing. Of course, you've got wind and sand and dirt and all that stuff to help out. There's a lot of other factors going into it. Okay, so here we go solving. We divide by 500. So you get 4/5 equals e to the negative 0.0244 t. Do you feel like you can do these in your sleep? No?
No?
Okay, take the natural log of both sides. We get negative 0.0244 t. So t then is natural log 4/5 divided by negative 0.0244. Remember, t is in years again. Keep up with your units so you know what you're talking about. So the natural log of 4/5. Again, on a test, if you don't have a calculator, I realize you have to stop right here. Divided by negative 0.0244. So it's going to take approximately 9.14 years for it to go from 500 grams down to 400 grams. Okay? All right, and then the last little part, E. E says, what is the half-life? So you have A of t equals 500 e to the negative 0.0244 t. And the question is, what is the half-life? Half-life means when will you have half this amount? What are you going to do, everybody? Put 250 for the future amount. Half the amount equals 500 e to the negative 0.0244 t. Half-life. I'm not going to finish that. Just make sure we can set it up. All right, everybody got it? All right, I want to look at the words in a problem that doesn't lead you through that so much. Okay, let's go to problem number 9. Problem number 9. The half-life of radium is 1,690 years. It takes a while. If 10 grams are present now, how much will be present in 50 years? Okay, this is telling you that this is a radioactive decay. It tells you the half-life It tells you initially how much you have, and you're going to be looking for how much is there in 50 years. Okay? Get off the screen. All right, let's get this problem set up. Number 9. All right, you already know it's radioactive decay, and if you want to do PE to the RT, that's fine, or we'll do A of T equals A sub 0 E to the KT. We know that K is negative. All right, how much do we start out with? 10, so that helps us build our function. Now, how's the piece of information that 1 half-life is 1690 years? How am I going to use that in here? The half-life is 1,690 years. What's that going to, that's going to help me figure out the decay rate, isn't it? Because the future amount would be 5 when T is what? 1690. Okay? So this helps me find K. All right, because that's a given fact that I can put in there and then solve for K. Yes? Oh, I'm off the screen. Thank you very much. All right, so the fact that the half-life is 1,690 years, I can put that in the equation and I'll be able to solve for K. So once I know K, substitute right here, and then I'll be able to answer the question, how much is present in 50 years? All right, work very similar to the growth problem. By the way, as you know, archaeologists, one of the ways that when they dig up something, they know how old it is who's had archaeology? Who wants to tell me? How do they determine how old those bones are, or whatever it is they dig up?
Carbon dating. Carbon dating.
Carbon dating, carbon-14 dating, right? Carbon-14 has a real long half-life, and they know what that half-life is. They know what the decay rate is of carbon-14, so when they get some bones or whatever, they test it for how much carbon-14 is left there, then they can tell how old it is. Okay, so that is another application for your decay. All right, everybody good? Okay, we're going to jump off that and we are on our cumulative review. And let's look at some of this. Right, I'll just use this. Cumulative review. And we're going to look at the even problems again because your student solutions manual have the odd problems, but a couple of you have already asked to see a couple odd ones, and we'll certainly do that. Okay, we're going to jump right on, we're on page 501 and 502, and the first one we're looking at is number 2, where you're given a function. And I'm going to look at this problem right here. Number 2. Okay, let's make sure it's copied right. 2x squared minus 3x plus 1, and you're supposed to find f of 3. And f of 3 is just a plug and a chug, and let's see if you got that right. What do you think here? What is negative 9 plus 1? 8. So 18 minus 8 is 10. Good old arithmetic will get you every time. Everybody good? The next one, you were supposed to find f of negative x. You did the right thing, do your little set of parentheses. You plug the negative x inside parentheses. Now remember that negative x is the same thing as negative 1 times x. So negative x squared is the same thing as negative 1 times x quantity squared. So if you square negative 1, you're going to get a positive 1. So that would be 1x squared. So this part right here becomes positive x squared, which makes that first number positive. And then a negative times a negative is a positive, so that part's right and that part's right. Any questions, anybody? Be really careful with these minus x substituted in. Minus x means, if it helps, negative 1 times x. Okay? All right, and then the C part, f of x plus h. You put a x plus h in for x. That was perfect. You showed how you squared that. That was good. Came and stuck it in right here. Did you distribute correctly? That's looking right to me. And I believe that is perfect. How's that? Perfect. All right. Any questions on that, anybody? All right, let's look at number 4. And at the end, I'll come back and get your odd questions. Let's go to somebody else's paper so I don't pick on the same person all the time. Okay, number 4. Are these cumulative reviews getting easier? Yes and no.
Yeah, yes, because they start to do like more recent stuff.
More recent stuff?
Sometimes you forget stuff.
Yeah, you do. And that's the reason for the cumulative review, because once you get into calculus, we say, you're supposed to be good at this, so we'll just keep reinforcing it here. Okay, problem number 4, we're solving this equation. Would you say this is a linear equation, quadratic equation, or what? Linear, because you got an x to the first. So the first thing you did was carefully distribute your 3 and carefully distribute your 5. That much looks perfect. 4, excuse me, can't multitask here. And I got x equals negative 26. I will give that a perfect. And I also want to say your communication here is beautiful. You show every little step. You are good, good, good. Okay? Everybody good on that one? That seemed too easy, didn't it? All right, number 6. Let's see what that looks like. Number 6. Oops. Number 6. Want to be careful that when you have a function, you write it as a function. F of x is equal to minus x squared plus 2x minus 3. Does it open up or down? And everybody said down because
There's a negative.
y'all are good. Negative right there. And then to find the vertex, what's this negative b over 2a equal to? Let's make good mathematical statements.
X.
X. The x coordinate for the vertex is negative b over 2a, and I believe that's correct. And then to find the y value, you substituted in positive 1, and when you do that, that comes out to be,
Negative 2.
all right, let's double check that. That's minus, and remember without parentheses, the square goes only with the 1, plus 2 times 1 minus 3. So 1 squared is 1, and then you got the minus. So these negatives are killing y'all. Remember, minus x squared is not equal to minus x squared. Exponents only go with the variable it's next to. Okay? All right, so when we put this in, we get negative 1 plus 2 minus 3, and that looks like to me that is going to come out to be 2. Is that right? Negative 2. So the vertex is going to be the order pair 1, negative 2. Any questions on that so far? All right, be careful with those negatives. These are good problems to get you back on that. All right, axis of symmetry always goes right through the x-coordinate of the vertex, x equal to 1. That is an equation. D, the next part, the y-intercept and the x-intercepts. The y-intercept is always easy because you let x be 0. So the y-intercept is negative 3. The x-intercepts you always find by setting it equal to 0. Did you fizzle out fast on this problem or what?
Any real ones?
How are you going to look for x-intercepts, if any?
The quadratic formula
You try to
or
factor.
the discriminant.
Yeah. I was hoping it was going to factor. Is it not going to factor?
Yeah, because it opens down
Okay,
the
so
text.
check the discriminant,
I think.
which is b squared minus 4ac, and b squared is 4, a is negative 1, c is negative 3, so you get 4 minus 12 less than 0. And so, therefore, no real roots. Okay, you're right. So there are no x-intercepts, none. Everybody good on that? Questions? Okay, let's go to number 8. Number 8. Did I skip something?
Yeah, it was solved. when
Oh.
requested.
I'm sorry, let me go back. Whoops. Pick up the whole thing before I lose it. Okay, 6. The last part, B, was solve where is f of x less than or equal to 0. What would you say? You told me that the thing opens down. You told me the vertex is at 1, negative 2. All right, so let's just kind of put this in a coordinate system. 1, negative 2, the vertex is here. The y-intercept, you told me, is negative 3. The graph goes like this. And the question says, solve wherever f of x is less than or equal to 0. It's saying, name all values of x where this function is negative. So where is this function negative? Where are the y values negative? All of them. So x is everywhere. Everywhere x is less than, the y values are less than or equal to 0 for all values of x. Yes?
I have I have a problem with like finding the domain and range in like basically every problem.
Well, for this particular problem, for your domain, which is...
What is the domain? Like I don't
The
understand
domain
the
is...
concept.
Somebody tell them what the domain is.
What x
Oh,
values the
X
graph
values.
contains.
The domain is there any values for x that you could plug in that would make this function not work? Like division by 0, negatives under radicals. And you can put in any value for x here and get a y value, right? So your domain is x is all real. The range is looking at your y values. If this point right here is 1, negative 2, what is your biggest y value? Because your curve's going down like this. What's your biggest y value? Negative 2. They're all getting smaller after that. So your range is y is less than or equal to negative 2. Yes?
In some of them, you have to like factor it, and then you find what x is not equal to.
Right.
Which ones are those? Just the...
When you had the radical
Okay.
a fraction, her comment was, in case you missed it, sometimes you have to factor and see what x can't be. That's if it's in the denominator, because you can't divide by 0. Okay? All right, domains x's, ranges y. What are the x's, or what can they not be? Range, what y values are covered when you substitute those x values in. All right, you might want to go back at, I think it's chapter R, maybe, where you get into some domains. Chapter R or chapter 1. Practice those. All right, is that good, everybody? We're off 6. Okay, now we're going to part number 8. Number 8 is graph using transformations, and whoever's paper this was, what in the world would we do if we got this on a test? It said graph. What do we see here?
It start with the cube thing.
No effort. Okay, bad. I'll put bad on that. Let's look for another one. There's no names here, so I was able to get away with that on this TV. All right, number 8. Here's one. Ooh, and use colors. Good, good, good. All right. Okay, let's see here. So this person first did, looks like they first did y equals x cubed. And here is y equals x cubed, went through 0, 0, 1, 1, 0, negative 1, negative 1. Here is y equals x cubed in pencil, right? And then the next one is probably the vertical stretch. Was that what you did next?
It's on the other page, what I did next.
Oh, horizontal shift, vertical, is that the order you did it?
Yeah.
Okay, so the next thing you did was a horizontal shift to the left one. Okay, so because of this part right here, the next thing that was done is y equals x plus 1 cubed. All right, so here is this graph, and it was shifted to the left 1, and there it is in purple. So you just sent all this over 1 unit. The pencil goes over 1 unit. And you've got all your points down at the bottom. All right, the next thing you did after that was you did your vertical stretch. You did y equals 3 times x plus 1 cubed. All right, so you took your purple, and now you multiplied your y values by 3. So if this y value right here is at 1, by the time you multiply it by 3, wouldn't that put it up here? Isn't that correct? Let me make sure all that was. Oh, that was your 0 value. I got kind of lost here. Sorry. Let me put some numbers here. This is 1, 1. This one is negative 1, negative 1. Okay, then you shifted it to the left 1. So now we have the point left. This is going to be 0, 1. And this one is negative 1, 0. And this one is negative 2, negative 1. Okay, so now vertical stretch, you're going to multiply your y values by 3. There you go. Y values by 3. 0, 3. I should be doing that in a different color to follow your numbers around. 0, 3. And you multiply this y value by 1, so you're still right here. And this y value by 1, and you're at negative 2, negative 3. Perfect. Okay, and then the last thing you did was down by 2. Y equals 3x plus 1 cubed minus 2. So you took this green and you dropped it down 2. So this one came down 2. This one came down 2. We're in red now. This one came down 2. Looks good. And I would follow your points through. All right. So she did a left 1, stretch 3, and a shift down 2. Looks good. You guys are good at shifting, stretching, etc. All right, that was number 8. Let's go to number 10. Number 10. Whoops. Number 10. 10, 10, 10. Okay, here's number 10. Let's make sure it's copied right. 4x cubed plus 9x squared minus 30x minus 8. Perfect. Find the real zeros. What was the name of the theorem that was going on right here? What's the name of that theorem?
Possible rational.
Rational roots theorem, right. Define your possible rational roots. Okay, so the first thing you did was listed all of those possibilities. You did the p over the q bit. I was trying to figure out how you did that. 1 over 1, 1 over 2, 1 over 4. Oh, I see how you're doing. You're going through listing them all. And that's exactly what you want to do. And if you've got repeats, as you know, you don't have to double check and double check. Okay, so the first thing you did, by the way, did you think to check out x at 1 and plug in and see if that gave you a 0?
I did it too, though.
Excuse me?
I checked it at 2.
Oh, okay. All right, but just remember I said that if you ever just plug in a 1 for x and the thing equals 0, then you know immediately that's going to work. I don't believe that would work anyway. And so you found a positive 2. You list your coefficients in descending powers. put it in there, and so you got, so number 9, 10, find all the zeros. So you found 2 is a 0. So at this point, if that is a 0, what's a factor?
2 or -2. Like
X
minus.
minus 2 is a factor, and what's your depressed equation that you're left with?
2.
By the way, shouldn't that have been a 4 when you came down?
Yeah.
Yeah.
That should be 4.
It's still.
Whoa, let's try this again. Not quite sure how you...
Yeah, I don't know how
Did you
to
do?
what I was doing.
Okay, bring the 4 down. 4 times 2 is 8. 9 and 8 is 17. 17 times 2 is 34.
What'd you do?
When you add, you get 4. 4 times 2 is 8. 0.
It still works.
I don't know.
Somehow you looked up by doing it
I
wrong.
think because I was like doing 2 into 2, and then I just like got confused by finding the factor of 4. So I probably just
Huh?
did that.
Huh?
Found the factor of 4, just 2 into 2, which is why I brought 2 down. That's probably what I did.
Yeah, you said 2 times 2 is 4.
Were you confused?
All right, but let's go here. Your depressed equation leaves you with 4x squared plus 17x plus 4,
What's next?
and you can either factor that or jump on a quadratic formula to help you out, but this does factor to, what, 4x plus 1 and x plus 4. Once you get here, this is going to be a great help for finding your zeros. Remember, your zeros is what makes your y value equal to 0. So that would be at x equal to 2, x equal -1/4, x equal -4. You need to get it written in its factored form so that you can find those zeros. All right. Might want to look back over synthetic division. All right, we're going to have to stop there, and we will pick up at the beginning of the next lecture. And then we'll go into trig. All right, take a break, everybody. All right, no, let's don't ask. Welcome back, everybody. We're on Lecture 16B, and we're going to finish our cumulative review, and then we're going to finally get into the trig. Hopefully, we only do one objective in 6.1, so hopefully we get that covered today, and then we're going to move into 6.2, and we're going to be looking at right triangle trigonometry as opposed to unit circle trigonometry. We'll hit unit circle a little bit when we graph our trig functions, but we'll start out with all of our vocabulary and definitions based on right triangle trigonometry. And that's because we're in a pre-calculus leading to the non-engineering calculus. We have forestry majors, and they need to be able to draw a triangle and figure out how tall the tree is, and we have all kinds of applications more for right triangle trigonometry. Okay, so we are picking up on the cumulative review, and I believe we left off at number 10. Did we finish number 10? No, we didn't. Okay, so let's go back to number 10 on the cumulative review. We're on page 502, and the thing that we had to do was find our real zeros. And then in part B, let's see, we're going to turn the page. Nope, we don't have that there. Part B, you were asked to find the intercepts of the graph. Well, we already know the x-intercepts because the x-intercepts are the real zeros, correct? Those are just the words for x-intercepts. So the x-intercepts are what make your y value 0. And what's your y-intercept? -8. You just read it right off your function. Let x be 0. The y-intercept is -8. Okay, so part C, we're supposed to now, D, sketch the graph by hand. And by the way, what was the degree of this polynomial? Third degree. What do you know about the end behavior?
One's up,
One's up and one's down. The positive in front of the x cubed means that as x gets big, y is big. As x gets small, y is small. All right, so we're just going to do a quick sketch of this. We can only do a sketch because we're not using a calculator. The zeros are at 2, -1/4, right? And -4. The y-intercept is down here at -8. By the way, when we wrote this in factored form, there were no even exponents on any of these factors. Remember, if there was an even exponent, like a square or fourth, when it would touch that number, wouldn't it turn around and go back the same way? But since these are odd ones on here, we know it's just going to alternate. So we can quickly sketch this graph because the positive in front of the x cubed means it's going to fly off here. Between the zeros -1/4 and 2, it's got to hit a -8, so somehow or another it's got to come down like this. It's odd, you already know this side's got to go this way, and because there was not an even exponent on that -4, it's got to cross and go like this. Of course, you could always go through and check some points. Once you have it in factored form, you could pick a number bigger than 2, such as 10, and put in for your x, and you see your y values are positive. You've already picked a number 0 between -1/4 and 2, so that took care of that. You could pick something like a -2. You put a -2 in here. This is negative, negative, positive, and that's why you're up above the x-axis there. Okay, so you could do a sign chart. Everybody good on that? Okay, number 10, we're good. Let's go to number 12. Number 12. 12. Okay, here's number 12. Number 12 is solving, what kind of equation do we call this? Might need to go in just a little bit more. What do you call this equation? Exponential equation. The variables are in the exponent. And what you recalled was if I can get the bases to be the same, then I'm going to set the exponents equal to each other. Okay, so the first thing you noticed, you had a 4 to 8. So you chose to make bases of 2. 4 is 2 squared, and 8 is 2 cubed. And then you did power of a power. Some people would write this like 2 squared like this, raised to the x minus 3. And then power of a power meant you would multiply that. You did that right there. And the same thing with the 8, write it as a 2 cubed raised to the 2x. Okay, but you work that down, you got x equals to -3/2. That looks, do you want the word perfect on there?
How about awesome?
Awesome. How's that? All right, perfect, awesome. Everybody good? And number 14 is the next one. Let's see what we have here. 14. Okay, number 14 says, suppose you are 14, given this function, 14, log to the base 3 of x plus 2, solve, where the function is 0. How did you solve that? I don't see the steps for solving. How do you solve this, everybody? 0 equals log to the base 3 of x plus 2. How do you solve it?
0 equals x plus 2. And then
Okay, what kind of equation is that? Use the words.
Log.
Log. I've got to get to the argument, which is a variable. That tells you need to switch it into exponential form. 3 to the 0 equals x plus 2. 3 to the 0 is 1. So x is equal to -1. Show your work how you get there. Okay? All right, by the way, while we're here, let's do a graph of this. What is the graph of y equals log to the base 3 of x? What does that look like? Yeah, it's going to go through 0, 1. Okay, so now what is the graph of y equals log to the base 3 of x plus 2 look like? What does that tell you to do?
Shift it to the left.
Shift it to the left 2. So everything's going to go over 2. Remember, this was your asymptote, so we'll just kind of carry it over here. And we're going to shift that over 2, and it's going to go like this. So there is your x equals -1 when y is 0. This is the x and y axis. And then here is your graph. Everybody got it? Okay. B says, when is this function bigger than 0? When is the y value, for what value of x is the y value greater than 0? For what values of x? Well, when x is greater than -1, all the curve is up above the x-axis. Is that clear? All right, and C says set the function equal to 3. Not quite sure how you're doing this so fast without showing all your steps, and on the test I'd go, how? I probably wrote that on some of your tests already, hadn't I? I would go, how'd you do this? Okay, so how did you do this?
3 to the third equals x plus 2.
Okay, it was a log equation, so you switched to exponential form.
3 to the third is 27.
27 equals x plus 2, so x is 25. Perfect. Be sure you communicate your steps on how you're doing this. Okay, good? Alrighty. Questions, anybody on 14? And that is it, except that you asked me to do number
I asked you to do 13.
13. You asked me, yes. Okay. Let's go look at number 13. 13 is solve. That's a very good question, especially since this is on your next test. We're going to solve this equation. 2x equals log to the base 9 of 9. Okay, as I wrote this down and I was listening to myself, I heard log to the base 3, log to the base 3, and all of a sudden I heard log to the base 9 of 9. Did y'all catch the bases changed? So when I noticed all of a sudden this is a 9, did any little identity come to mind here? What is that equal to? 1. Okay, that's one of your identities, log to the base m of m. Okay. All right, so now we have log. This is a good question. Very good. All right, now we have a log equation. We've got to solve for x. Can I just go jump into exponential form? No, because I got two terms over here. Actually, there is a way, but it's not the simplest way. Okay, so what property can I use to get rid of this plus that's right here? Okay, so we're going to have log to the base 3 of x plus 1 times 2x minus 3 equals 1. Okay, I'm using the property that the log to the base a of m times n is log to the base a of m plus log to the base a of n. Everybody remember that property? All right, so let's multiply that out. That's log to the base 3. When I multiply this out, that looks like a 2x squared. Negative 3 plus 2 is a minus x minus 3. Does that sound good? Okay, so I have log to the base 3 of this quadratic equals 1. And I've got to find some way to get rid of that log there so that I can get to the x. What are you going to do? Okay, you're going to switch it to exponential form. So we have 2x squared minus x minus 3 equals 3 to the first, which is 3. All right, what kind of equation is this? Name it. Quadratic. Okay, so to solve a quadratic equation, we need what over here? 0. 2x squared minus x minus 6 equals 0. I'm really going to hope that this factors, does it?
Yeah.
Okay, 2x, if it didn't factor, what would you do? Jump on the quadratic formula very quickly. All right, you asked this, so have I lost you yet? Okay, so we'll set each factor equal to 0, so x is minus 3 halves and x is positive 2. And are we going to circle this and say we're all done?
Yep.
No. Where's that red pen?
Oh,
What's the
there's
word?
no next-
Alert.
Extraneous.
Extraneous. Extraneous. Roots. All right.
My bad.
Remember, you can't take the log of a negative number. So negative 3/2 is negative 1.5. So if you try to put a negative 1.5 in here, your original equation is going to blow up. That's a fake root that came in because you applied some properties and introduced something that may not be real. If you put a 2 in, all your arguments are positive and you can be pretty confident that that will be your answer. Okay? Pass that red pen back for the alerts. All right, are we good? Everybody good? Yeah.
Number 7.
Number 7, okay. Number 7. Oh, I like number 7. Number 7 would be a really good exam question. Okay, we're looking for a quadratic function. And on this quadratic function, they told us the vertex and the y-intercept. Did you have a question?
If you could check that on my homework paper.
Check number 7 on your homework paper. Do you remember what yours looked like real fast?
It's
And all the
colorful.
colors.
I see it.
Rainbow woman.
7. Oh, I like the way you started out. Okay. All right. So the information on number 7 is that you've got a y-intercept and you got a vertex. So by request, we're going to look at this problem. The first thing she wrote out, which is absolutely perfect, is a general formula for a quadratic function. The other general formula that you looked at for a quadratic function where you'd see your shifts and everything was a times what? Squared plus k, where your vertex is hk. Okay? All right, those are just that's just an add-on. So you're fine. I'm just going to mention that there were 2 forms that you looked at, and this might be a easy form to jump on. Okay, let's see what you did here. Given that the graph has vertex 4, -8, and passes through the point 0, 24. My guess is that you might have made it a little harder than you needed to. This is definitely a place you want to start out because now you have that f of x equals ax squared plus bx plus 24. No, I guess you had to go that way if you were going to do it this way. All right, so you know that f of 4 is -8. I'm sorry, I'm trying to figure out what you're doing. It was like you eventually got it. I think what you were trying to do is say the x-coordinate of the vertex is -b over 2a. That got you to there. And then, what is this part right here? I'm lost. Oh,
Cookie.
you saw for b. b is -8a. Okay, all right. So, it'll take me just a second here. So we're here. you said B is the same thing as negative 8A, so my guess is you went and put a negative 8A for A there. And you knew the X was 4. And you knew the Y value was negative 8. Okay, I figured out what you did now. So after you knew B was minus 8A, you're down to f of x equals ax squared plus, and in the place of B, you're putting a minus 8ax plus 24. Just made that substitution right there. Perfect. All right, then you said, okay, so now I'm going to use this point that I'm given that when x is 4, y is 8, negative 8. So you put negative 8 in for y, and this will help you solve for a. That's perfectly fine. A, and in the place of your x, you put your 4. You did this, I'm just kind of reiterating here what you did. Minus 8a, and in the place of x, you're putting 4 plus 24. And so when you solve that down, you find a. Okay, that's a perfectly fine way to do it. The reason I went back up here is because since you're given the vertex, it's going to be a lot easier if you use that form of the quadratic equation. All right, so your way was fine. Everybody with me what she did? Okay, let's go the easy way real fast. I think it's the easy way. One of your forms for your quadratic function is this, where the vertex is hk. All right, so if you already knew the vertex was 4, negative 8, using the point 4, negative 8 for the vertex, you already had half your battle. F of x is equal to a times what? X minus 4 squared minus 8. Okay?
We have an x.
Excuse me?
For the 0.024.
So now, okay, so the vertex got us this far. And we don't know the a, but we also know that we have the point 0.024 on the graph. So if we'll let f of x be 24, x is 0, now we'll easily be able to solve for a. So we get 24 equals a times 16 minus 8. 16a, we'll add 8 to both sides. I guess that's 32. So a then is equal to 2. And so the question just asked for a quadratic function. It didn't say that you had to put it in any particular form. So I would quit at writing it at 2 times x minus 4 squared minus 8. Okay? Once you find out a is 2, you can just put it right back there. All right, your way was fine. You got there. I think your way was probably just a...
But look at the work. Like looks like it's less work. You just
Oh.
did it with the second one.
Yeah, right. We're always looking for the least amount of work. So just know that you have 2 forms for a quadratic function. And you use whichever one of those forms works best for you. But if you know a vertex, this is going to get you there a lot quicker. Okay, is that good? All right, thank you for showing me that. That was a good way to do it. And it looks like you were really smart because you did so much work. Okay? All right, is everybody good now on cumulative review?
11.
Number 11?
Yeah. I couldn't figure it out.
Do you want me to pull your paper?
Yeah, I tried it and I left. I think the page should be there.
Let's see if I can. Okay. Oops.
If it's even there, I don't know.
Did you turn in number 11?
I tried it.
Okay, I don't see it on here. We'll just do it together. Number 11. Okay. Number 11, you're given the function g of x equals 3 to the x plus 2. And you're supposed to graph it using transformation. Oh, I love this problem. Number 11. We're going to graph it using transformations. We're going to state the domains, ranges, and the horizontal asymptotes. And we're going to find the inverse and the domain, range, and vertical asymptotes of the inverse. And then we're going to graph it. This is a great problem. Great, great, great. Alrighty. What basic function are you going to start out with? I'll just call it basic. Y equals 3 to the x. Okay, what does y equal 3 to the x look like, everybody? Fingers in the air. What does y equal 3 to the x look like? Aaron, I don't believe that was quite right, was it?
That's what I did.
Okay, y equals 3 to the x. Goes through 0, 1, right? What's your asymptote?
0, x equals 0.
Y equal to, here for the basic. Y equals 0.
Oh, okay.
And we're on the basic. Okay, now what are we going to do to this basic to get this one?
Shift up.
We're going to go up 2, a vertical shift up 2. So we're going to go up 2, so your asymptote is actually going to go up 2 also. So we go from 0, 1, 2, put your asymptote up here. Y equal to 2. Everything goes up 2 units, and the graph's going to look like this. All right, so there's my graph. That's all you need to do is keep up with that point 0, 1 and move it around. So problem number A says graph it. What is my domain here? What? I'm going to ask you every time domain till you get it right. Thank you.
Good job.
Because you can raise 3 to any power and add 2 to it. Range is what are the y values that are covered. Y is,
Bigger than what?
this is your asymptote at 2.
Oh. Yeah.
Greater than 2. All your y values are greater than 2. Yes.
So if you put for the domain infinity, infinity, and
That's
then 2
fine.
to infinity, okay.
If you want to put an interval notation, it would look like that.
Yeah.
Yeah. Is that good? Okay, and then the next part says horizontal asymptote for G, y equal to 2. Horizontal asymptote. Everybody got it?
For the range, it wouldn't be y is greater than and equal to 2, right? It'd just be greater than.
Strictly greater than, because 3 to the x is always some number bigger than 0. So some number bigger than 0 plus 2 is always got to be bigger than 2. This thing will never exactly equal 2.
When do you write equal to? Greater than or equal to?
Well, that might be under a square root, like square root of x minus 2. Square root of x minus 2. Your domain is x is greater than or equal to 2. Okay. All right, B part, determine the inverse. I love doing this on test. What are you going to do? This is 1 to 1, so you know it has an inverse. So what do I do to solve?
Swap your x and y.
Interchange x and y. What kind of equation do I now have?
Inverse.
Well, the start of an inverse, but it's got to. I got to solve for y, and that's up in the exponent. So I got to find a way to get it. All right. So what's my first step in solving for y? What's the first step?
Get it on the side by itself.
Get it on the side by itself. So let's subtract 2 from both sides. What do I do now?
Log.
Okay, convert it to log form. So we have log to what base? 3 of, and then give it its proper notation. You can be pretty sure you're going to have problems like this on a test and an exam. Okay. All right. So the inverse of an exponential function is going to be a log function. All right. We want to look at the domain, the range, and the vertical asymptote. Well, before we even graph this, we know the domain of G becomes what?
The range of the.
Yes, the range here is y is all real numbers. We know the range of G becomes the domain here, x greater than 2. And the asymptote here is y equal to 2, so the asymptote down here is x equal to 2. And you can always find it from right here. Whatever you're taking the log of, it must be greater than 0. X minus 2 has to be greater than 0 because you can't take the log of a negative number, so x had to be greater than 2, which meant that your asymptote was x equal to 2. Got it? Okay, so part C says sketch it on the same axes. I probably didn't leave enough space, did I? Is that red? What happened to my red pen? You guys got it? Oh, right here, thanks. All right, so we'll put an asymptote over here at x equal to 2. By the way, remember y equals log to the base 3 of x. I'm just going to put it right here. Remember, it's going to go through 1, 0. Looks like this. So it's really this graph just shifted over 2 to the right by transformations, 2 to the right. So the axis comes over. So what's this x-intercept right here going to be? 3, 0. Just move the whole thing over. And it looks like this. Okay? How's that? Good? Everybody good? All right, another question on cumulative review that ran you crazy? That's a very good question. I usually try to put those on test, kinds of stuff. All right, let's jump over to Chapter 6, Section 1. We're starting our trig for the rest of the course. And you only have one objective out of 5 that we're going to hold you responsible for. And again, this course was designed with in mind that you're headed to Math 121 or 131 Calculus. And in 6.1, all we're going to do is learn about degrees, angles, and standard position. Angles and standard position, the degrees, how to convert from degrees to radians, radians to degrees. That's all we need out of 6.1. Okay? All right, so I called this degrees, radians, angles, and standard position because we have to get our vocabulary straight. So 6.1. 6.1. Angles in standard position. Who can tell me what that is? Where's the initial side of the angle?
At the origin.
On the positive x-axis. So this is called the initial side along the positive x-axis. Okay, which way is positive when you're finding your angle? Which way do you go? This way is positive angle direction. Okay, so if I were going to go about 45 degrees, I would go like this. This is approximately 45 degrees. And this part is, if this side is called the initial side, this side is called the terminal side of our angle. Okay. So an angle in standard position has the initial side along the positive x-axis. If we're looking for a positive angle, we rotate counterclockwise, and wherever we stop is the terminal side. Suppose I have an angle in standard position and it goes all the way to the y-axis. How many degrees would that be? 90 degrees. Suppose I have an angle in standard position and it goes all the way to the negative x-axis. How many degrees?
180.
180. Suppose I have an angle in standard position and it goes all the way to the negative y-axis. How many?
270.
270 degrees. Suppose I have an angle in standard position and it comes all the way back around to the positive x-axis.
360.
360 degrees. Aren't y'all having fun? Suppose I have an angle in standard position. I start here and I go all the way around and then stop. Okay, I have an angle of 720 degrees when you go round and around and around. All right, everybody good so far? Okay, let's see if you really are. I want you to draw an angle in standard position that represents negative 225 degrees. I want to know where that terminal side is. Draw an angle in standard position that represents negative 225 degrees. Okay, I'm starting along the positive x-axis. Which way am I going? Up or down?
Down.
Down is negative. The negative means you're going in a negative direction.
Is it gonna be in the third quadrant?
1, 2, 3. Okay, let's see. If I go this far, how far have I gone?
90.
Negative 90. If I've gone this far, how far have I gone?
Negative 80.
Negative 180. This would be negative 180. This is going to be negative 270, so where am I going to stop?
45 degrees out.
Somewhere over here. So here is my angle. This big angle right here represents negative 125 degrees. Okay, everybody got that? Excuse me?
120.
Did I say 125? I'm sorry, 225. Negative 225 degrees. Negative 225 degrees. Okay. Where would I find negative 100 degrees? Where's the terminal side of an angle in standard position of negative 100 degrees?
Third quadrant.
Third quadrant. This would be negative 90, negative 100, right here. Okay, everybody got it? The negative just is telling you the direction. All right. Are we okay? Okay. Let's go to a circle of radius 1. So here we have a circle of radius 1. Oops. And the center is at the origin. What is the circumference of this circle? 360 degrees, okay. What else did you memorize as a formula for a circumference of a circle? No, that's area. 2 pi r, and in this case our r is 1. So for our circle, if we had a radius of 1, if I go all the way around, I've gone 360 degrees. But the formula you memorized for circumference of a circle a long time ago was 2 pi r. Well, what that was telling you is that this 2 pi is an angle measure. And it's called a real number measure. A real number measure, because pi is 3.14. So 2 times 3.14, it's a real number measure. But when we have an angle in real number measure, it's called radians. So we have two ways that we're going to express angles. We're going to measure angles in degrees and angles in radians. Okay, and there's other ways to represent angles too, but we're only responsible for degrees and radians. Okay, so the reason I wrote this up here is because if I had a circle of radius 1 and I go all the way around, I get 360 degrees. If I were doing it in radian measure with that, it would be equivalent to 2 pi. So we could say that the ratio 2 pi to 360 is an equivalent of 1 because 2 pi radians is equal to 360 degrees. Or pi is equivalent to 180 degrees. So if this is 2 pi all the way around, if you just go halfway around, you've gone 180 degrees or pi radians. pi radians. So this little factor, pi over 180, or you could do 180 over pi, is going to be the factor for converting. You're either going to use pi over 180 or 180 over pi. I mean, you could use 360 over 2 pi, but why use the big numbers if it reduces? Okay, this is just kind of standard. All right, so let's convert from degrees to radians. Okay, let's start with 90 degrees. All right, 90 degrees. We want to represent that in radian measure. So we're either going to use pi over 180 or 180 over pi as our conversion. Well, if we're wanting to go to radians, we would like the degrees to cancel out, right? We need to get rid of the degrees. So we'll use our factor pi over 180 degrees. The little degrees divide out. And we have 90 pi over 180, or that reduces to pi over 2. So 90 degrees, if you were putting your angle in standard position, that's 90 degrees. This is equivalent to pi over 2 radians. Okay, just like if you had 180 degrees, that would be equivalent to pi radians. Do you see how that works? That's 180 degrees. And that's half of the whole 2 pi, so that equals pi radians. Okay? Suppose we have radians and we want to convert to degrees. Convert radians to degrees. For example, pi over 3. Pi over 3 is radian measures. And we want it to convert to degrees. So we're going to do pi over 180 degrees or 180 degrees over pi, because I need to get degrees in my answer. Yeah, we want to multiply this times 180 degrees over pi, because we want answer with the degrees in there. And in this case, the pi's divide out, and we get 180 degrees divided by 3, or 60 degrees. Which quadrant is the terminal side of this angle in? Angle in standard position, which quadrant is it in?
1.
60 degrees. This is 90. 60, the terminal side would have to be here. 60 degrees. Okay. Convert 5 radians to degrees. 5 radians. I want you to tell me, before we even do this, where you think the terminal side is.
On the x-axis, negative.
Okay, what's pi approximately equal to? 3.14. So 5 radians is definitely bigger than 3.14.
Well,
Okay, 2 pi would be approximately what? Double 3.14. 6.28. Okay, let's see what's down here.
3 pi over 2.
What's pi over 2 radians, or 90 degrees? What's half of 3.14?
1.7.
1.57? So if you start here at 0, you go to 1.57, go to 3.14. To get here, just add those two numbers together. Then they come out to be something like 4.78. Isn't that right?
7.1.
3.14 plus 1.57. 4.71. Okay, radians. All right. All I did was say 3.14 and I added a 90 degrees or a pi over 2 to that. All right, so where's the terminal side of 5 radians going to be? Angle in standard position, 5 radians, come all the way around in here somewhere, 5 radians. So when we convert this to degrees, wouldn't we expect this to be between 270 and 360? This is 180, 270, 360. It's going to be down here somewhere. All right, let's convert 5 radians to degrees. You're going to multiply 5 times what?
Pi over 180.
No, I need degrees in my answer.
1 over pi.
180 degrees over pi. Let's just plug that in the calculator and see what we get. 5 times 180 divided by pi, and that comes out to be approximately 286 degrees. There it is right there if you can see it. I did 5 times 180, divided that by pi, and it came out to be about 286 degrees. So 5 radians is equivalent to about 286 degrees. Okay, everybody good? Converting from degrees to radians, radians to degrees. All right, let's see if we can't start in section 6.2. Got a lot of objectives in 6.2. Your homework for 6.1 is just converting from degrees to radians, radians to degrees, knowing where the terminal sides are. Okay, 6.2. Just as a start. Whoops. What time's this class over? I forgot. 12:30. We'll just quickly look at this and we'll work real hard tomorrow. We're going to work on right triangle trigonometry. And we want to learn to find the values of the trig functions of an acute angle. What's an acute angle?
Less than 90.
Less than 90, between 0 and 90. Okay, we've got some identities. Oh, up here preparing for this section, it talks about a Pythagorean theorem. What's that about?
A squared plus B squared equals C squared.
A squared plus B squared equals C squared. What does that relate to?
The two sides squared.
Right triangle. The legs of a right triangle, A and B, and the hypotenuse is C. Okay. So what's going to happen is we're going to look at a right triangle, and we're going to give it names with respect to an angle. If that's angle theta, that is called the adjacent side of theta.
It's easy.
And if you're looking at this theta opposite it, that is called the opposite side. And the hypotenuse is always the side opposite the right angle. And if you look on the bottom of page 611, all of your trig functions for the angle are defined in terms of opposites, hypotenuse, adjacents. If you haven't done this before, start looking for a way to memorize these, and then we'll be applying them. Okay, we've run out of time, so we're going to need to stop right here, and we will pick up at 6.